Modern electronics and our renewable energy systems operate because we can fundamentally manipulate materials at the atomic level. This relies on the Bohr model. At the center is a nucleus of protons and neutrons, surrounded by electrons orbiting in discrete shells. The outermost ring is the valence shell. Electrons located here are the primary participants in chemical bonding and electrical conduction. While valence electrons are typically bound to the atom, electricity requires them to break free and move through the material. To determine if a material will conduct or resist this movement, we have to look at the specific energy states available to these outer electrons. In a solid crystal, individual energy levels merge into two primary bands. The valence band contains the electrons bound to the atoms, while the higher energy conduction band contains the electrons free to move. In a conductor like copper, these two bands overlap. Because there is no gap, valence electrons move into the conduction band with minimal energy input. Insulators, such as glass, have a massive forbidden gap between the bands. Electrons are trapped in the valence band because they cannot acquire enough energy to cross this void. Semiconductors, such as silicon, possess a narrow gap. While they act as insulators at absolute zero, an injection of thermal energy or light is sufficient to knock electrons into the conduction band. This ability to switch a material from an insulator to a conductor is the technical requirement for all modern solid-state electronics. Silicon is the primary material used to build these devices. It replaced early germanium components because it is the second most abundant element in the Earth's crust. It operates at higher temperatures without leaking current, and it easily forms a stable insulating oxide layer. Silicon has 4 valence electrons. It shares these with 4 neighboring atoms to create covalent bonds, resulting in a stable, 3-dimensional diamond cubic lattice. When thermal energy breaks one of these bonds, an electron is promoted to the conduction band and moves through the crystal. This is electron current. The vacancy left behind in the covalent bond is called a hole. If a neighboring bound electron moves to fill that spot, it leaves a new hole where it used to be. This makes the vacancy appear to migrate through the crystal as a positive charge carrier. Current in a semiconductor is therefore a dual system, negative electrons moving through the conduction band and positive holes moving through the valence band. Pure silicon is a poor conductor at room temperature. To control its electrical properties, we must add specific impurities in a process called doping. Injecting the pentavalent atom like phosphorus introduces 5 valence electrons. 4 of them form bonds with the silicon lattice, leaving the 5th electron unbound and free to move. This creates an N-type semiconductor, where these extra free electrons are the majority charge carriers. Conversely, injecting a trivalent atom like boron creates a vacant state in the lattice because boron only has 3 valence electrons to share. This is a P-type semiconductor, where the majority carriers are positive holes. By doping silicon, we can create materials with specific asymmetric electrical profiles. When an N-type material is joined with a P-type material, they form a PN junction. At the border, free electrons from the N side diffuse across the junction to fill the available holes on the P side. This movement leaves behind fixed positive and negative ions at the border, creating a wall of charge known as the depletion region. This region generates an internal electric field that prevents further electrons from crossing. In silicon, this barrier potential is approximately 0.7 volts. We can manipulate this barrier with an external voltage. Forward bias shrinks the depletion region to allow current, while reverse bias widens it to stop the flow. This directional control of electrons is the mechanical basis for the diode, the transistor, and the solar cell. A commercial solar panel is a large-scale application of this junction. It is a flattened PN junction designed to capture photons. When a photon hits the depletion region, it knocks an electron into the conduction band, creating an electron-hole pair. The internal electric field forces the electron to the N side and the hole to the P side. It must travel through an external wire to return. This forced movement of electrons through the wire provides the usable current for the power grid. By utilizing the asynechic nature of the PN junction, we convert sunlight into a directional flow of electricity. This same physics scales from these large solar arrays to the billions of microscopic transistors on a single computer chip. It is the result of isolating the energy states of a single atom and using them to engineer the behavior of a crystal lattice. By forcing electrons to follow a specific path across these junctions, we have created the physical requirements for both the global processor network and the renewable energy grid.